Hello, in this video we are going to see how we can use a differential equation to develop a Maclaurin or a Taylor polynomial for a function. We are going to assume that we have a first order differential equation with initial condition. Let's say we have dy dx is the same as some function h of x and y, and then the condition that y at some point x0 takes the value y0. Depending on how the function h of x and y looks like, we may or not be able to obtain explicit particular solution for y. However, if this function y we are trying to find has necessary derivatives, so if we could know beforehand that we can take many derivatives of that function, we can determine the Taylor polynomial, let's say of degree n, that approximates the particular solution y close to x0. If we are trying to find the Taylor polynomial of y centered at x0, we are going to need to have the following pieces of information. We need to know what is the value of y at x0, and that we know is y0. Then we need to know what is the value of the derivative of y evaluated at x0, and that is by definition the function h evaluated at x0, y0. We need to know what is the second derivative of y evaluated at x0, so that means we need to know also what is the derivative with respect to x of the function h, which is a function of x and y, evaluated at x0, y0, and so on. So we need to find in general, up to degree n, what will be the n derivative of y evaluated at x0. So we found the first one, the value of the function at x0, that's given. We can find the value of the first derivative at x0. And we need to see in general how do we do this, so we can complete the Taylor polynomial of y of degree n centered at x0. And we do this by taking derivatives of the function h and evaluating them at x0, y0. Once we are done with this, then we have all the ingredients we need to write the Taylor polynomial of degree n as, well, the first term is y at x0. Then we are going to have the derivative of y at x0, so the function h evaluated at x0, y0, multiplied by x minus x0, plus the second derivative, that's the derivative of h with respect to x evaluated at x0, y0. That has to be multiplied by x minus x0 squared and also divided by 2 factorial, so by 2, and so on. I ran out of space, but I'll write the n term over here. We are going to need to write what is the n derivative of y at x0. We are going to multiply that by x minus x0 to the power of n, and then we need to divide that by n factorial. So we have actually all the ingredients that we need to attempt to write the Taylor polynomial that we want. So let's do that. We want to find the Maclaurin series for y up to and including the term in x squared, and the differential equation that defines y is dy dx has to be the same as y squared divided by 1 plus x. We have the initial condition that y at 0 is 1, and we are considering values of x greater than -1. So we are not trying to solve this differential equation, we are just trying to find what the derivatives are, so we can put together the Maclaurin series. Let's write over here that, well, we can call it maybe p20 of x, so it's a polynomial of degree 2 centered at 0. So for the first term, we need to write what is the value of the function at 1, so that's just, at 0. That is 1. Then for the next term, we are summing the value of the function, the derivative of the function at 0, multiplied by x, and then we need the second derivative of the function evaluated at 0, multiplied by x squared and divide by 2. When we want to find the value of the derivative at 0, that means we are evaluating the derivative at the point 0, 1. So I can write with the notation we have originally dy dx evaluated at 0, 1. This is going to be 1 squared divided by 1 plus 0. So this is equal to 1 as well. So let me write the next term, 1 plus x, and then plus, if for the next one, we need to consider the derivative with respect to x of the derivative of y with respect to x. And then we need to evaluate this at 0, 1. So let's find what this derivative is. We need to take the derivative with respect to x of y squared divided by 1 plus x. And then we're going to evaluate this at the point we want. Now, quotient rule, we need to take the derivative of y squared with respect to x. I'll write it and then we'll do it. And then we need to multiply this by 1 plus x, then minus. We are going to have the numerator y squared multiplied by, I'll write this directly, the derivative of 1 plus x with respect to x. That's just derivative of x with respect to x, so it's 1. And then all of this is going to be divided by 1 plus x squared and evaluated at 0, 1. This is, we are applying the chain rule over here, 2 times y times the derivative of y with respect to x. So that's the result of applying the chain rule to y squared when we take the derivative with respect to x, times 1 plus x minus y squared, and all of this divided by 1 plus x squared. And we need to evaluate this at 0, 1. So this is 2 times y times the derivative of y with respect to x, that's y squared divided by 1 plus x. And then we are multiplying by 1 plus x, and then minus y squared. All of this divided by 1 plus x squared, and we need to evaluate this at 0, 1. So over here we have a factor of 1 plus x that cancels. And if we want to write actually what the derivative is, so we have 2y cubed minus y squared over 1 plus x, all of that square, evaluated at 0, 1. And that is going to give us, on the numerator, we have 2 times 1 minus 1, so just 1. And then divided by 1 plus 0, all of that square, so just 1. So the result of the second derivative evaluated at 0, 1 is just 1. So if we go back to our polynomial, then last term we are going to write is x squared divided by 2. So this is up to x squared and including x squared, the Maclaurin series for the solution y. We did not attempt to find the solution y. We just have a polynomial of degree 2 that approximates it close to x equals 0.